Okay, so hello everyone. My name is Simon Schnürch. I'm at the Fraunhofer Institute for Industrial Mathematics and the University of Kaiserslautern, and I present joint work with Ralf Korn about point and interval forecasts of death rates using neural networks. And first of all, I would like to give some motivation on why we should be interested in forecasting death rates, what are death rates, and why we might use a neural network for doing that. And first of all, I want to start with introducing the concept of longevity risk. So what is longevity risk? What is this about? For this, I have brought a quote by Jane Austen, which shows that longevity risk has been around for quite some time now. And the quote says, "People always live forever when there is any annuity to be paid them." An annuity is a very serious business. It comes over and over every year, and there is no getting rid of it. So an annuity is just a promise that one person makes to another person that some sum of money will be paid until the death of the person. Or in most cases, probably there will be a contract between an insurance company and a person, and then the person will get some money every month or every year, for example, from the beginning of the retirement until the death of the person. And annuities are a nice thing for the persons receiving the annuity, but they can be problematic for the person or institution paying the annuity. For example, if you as an insurance company assume that somebody is going to live 10 years and the person then lives 20 more years, then you probably are going to have a problem because you have to pay for a longer time, and so you have to pay more than you expected. And if you're an insurance company, you will have multiple contracts, so you will have to pay out many annuities. And if you underestimate the life expectancy of your clients on average, then again, you're going to have a big problem because you are going to incur multiple losses on average. And this risk of underestimating average future longevity is called longevity risk. And this is problematic, for example, for insurance companies. And there are several ways how you can deal with this risk. And we're going to focus on one way of dealing with longevity risk here, and that is improving mortality modeling. So if you have a better model for mortality and future longevity, then you can diminish this problem of underestimating future longevity. And the tools for this have been introduced in the 1990s. And you have to be a little cautious here because there are several things that influence mortality. And to give you an illustration for that, I have this picture showing the death rates of 10 countries. So we see some dependence on the age. We see the age range 0 to 100. And we see that death rates obviously also depend on the time. So here we see, for example, the years 1951 to 1960. And the color scheme just means we have red color for high death rates and blue color for low death rates. And I haven't really said what a death rate is so far. So if you don't know what it is exactly, you can just think of it as a 1 year probability of death. So it's very similar to that. So just a number that tells you how likely it is that a person of a given age will in a given year die within this year. So that's a very similar concept. And the picture we see here makes sense from this point of view, because, for example, we have higher death rates at higher ages. So probability of dying just increases with age from a certain age. And if I now start the animation, then we will move forward through time. Apparently I can't start the animation. Okay. Okay, then you will just have to trust me that if we would move forward through time here, so from 1960 towards 1970, 80, 90, and 2000, that mortality rates would decrease for all ages, basically. And in fact, they have decreased quite a lot, and often more than expected. So in many countries, projections and forecasts have been made for future death rates, and often the development of longevity has been underestimated by experts, by demographers, by actuaries, and by the models that had been used so far. And therefore, in the 1990s, a different concept came up, which is stochastic mortality modeling. So you take the stochasticity of future mortality rates into account, you get a distributional forecast, and you get more robust towards longevity, increasing longevity. And in order to prepare what I'm going to tell you next, I just want to tell you a little bit about these stochastic mortality models. So the most well-known stochastic mortality model is the one by Lee and Carter, and it just assumes that the logarithmic death rates, and they depend on age X, year T, and also on the population I, and the population is just a combination of country and sex here. So for example, all English and Welsh females, or all German males, or whatever. And this logarithmic death rate is modeled by a sum. So we have a basic age structure of mortality here. This parameter does not depend on time, it just depends on age, because age is clearly the most important factor when it comes to mortality that we have available. And then we have a second term here where we have the so-called period effect, kappa T, which depends on time and which just tells us how mortality evolves over time. And usually it has been mostly decreasing. So mortality has been decreasing over the past few decades. And then we also have this beta X term here, which is called the age effect, and which tells us something about age-specific mortality improvements. And as you can see, all these parameters depend on the population. So if you have multiple populations that you are modeling simultaneously, then you have just multiple models, which do not know anything about each other, basically. So there is no interaction and no interrelation between different models for different populations. The Lee-Carter model has worked quite well for certain populations, but there have been a lot of extensions to it. And one extension goes in this direction that I've been mentioning, basically, that you want to model multiple populations simultaneously, and you want to have interaction effects, because there are factors that affect the mortality of multiple populations simultaneously. And it just makes sense that there will be some common developments there that you should incorporate into the model. And one model is called the Augmented Common Factor model, ACF, and it gets its name from the common factor here. So you see the structure is very similar to the Lee-Carter model, but we just have a common factor, a common age period interaction term, which describes the common development of mortality. Another model is called the common age effect model, and I'm showing it here in the version of Venn and co-authors. And here we assume that the base structure of mortality is the same over all populations. And then we assume that there are multiple age period interaction terms. We just model multiple age period interaction terms. So we have one interaction term and then another one up to k interaction terms between age and period. So we just increase the number of parameters to allow for a better fit of the model. And again, here we assume that the age effects, so beta x1 up to beta xk, do not depend on the population. So they are all the same. What does depend on the population is the period effect here. Okay, and there are many, many more mortality models. And from this, you might already be able to see that they also have some drawbacks. One drawback is that the structures of these models sometimes seem a bit arbitrary. So why should we include this factor here? Why do we need k factors here? How many factors do we need? So there are some questions which are not easy to answer. And you could just take a different point of view and say, okay, maybe we should refrain from making such structural assumptions and instead try to go for a model which has a better predictive capability, perhaps. And this is the second point. As every model, these models have the drawback that they are not optimal in every situation. So just as an example, I have here the Lee-Carter forecasts. So Lee-Carter model calibrated on 10 or 20 years of data. For the population, for the female population of England and Wales. And we compare it to the ground truth in black for 10 years. And we see that for higher ages, so 89, 83, this looks okay. Both models look okay, but then for lower ages, there clearly is some divergence between the truth and the forecast. So the forecast is too optimistic, actually, in this case. And perhaps we can improve on the forecast for this population and also for other populations by using more sophisticated models. So to quickly summarize this somewhat lengthy introduction, we need mortality models for many applications. We need good mortality models, for example, for pension plans, insurance companies, governments. However, accurate mortality forecasts are not always achieved by classical methods. And with that, I mean expert judgment. I mean really classical methods used even before stochastic mortality models, but also stochastic mortality models themselves. However, an important point about good mortality forecasts is also that they should give an impression of the possible distribution of future mortality rates. Because, for example, we need that for risk management purposes in insurance companies, or for just evaluating the uncertainty related to the forecasts of our models. This is a very useful thing, and a model should give this. Stochastic mortality models achieve this, and therefore we want to try and achieve this with any model extension we propose here as well. And this leads me to the content of the talk. We propose to use a convolutional neural network for mortality forecasting, along with a reliable method for quantifying its prediction uncertainty. And then we're going to compare its performance to other neural network architectures and to the stochastic mortality models I have mentioned, so Lee-Corte and augmented common factor. Actually, machine learning has been applied quite a lot in mortality modeling and forecasting already. So there are a lot of applications of different methods, for example, Poisson regression tree boosting, cluster analysis, and different types of neural networks, such as feed-forward neural networks, recurrent neural networks. And we will consider those two as benchmarks here. But we will focus on a different type of neural network in this talk, which are convolutional neural networks. And usually, convolutional neural networks are applied for image data. So for example, if you want to classify images and say, okay, in this image we can see a dog, and in this image we can see a cat, and you want this done for many images, and you want a computer to do it, then you will use a convolutional neural network for that, probably. Or also if you want to detect objects in images. So whenever you have images, think CNN. And why would you do that? Well, because CNNs are good at capturing two-dimensional structure in data. And of course, obviously for images, the two-dimensional structure of an image is very important to say what's in the image. And now you may be asking yourself, why should we apply this to mortality data? And I'm going to try to motivate it. So if we have a look at this heat map again, then we see that there are two dimensions here as well. We have the age dimension and we have the year dimension. And mortality rates do not only depend on age or year alone, so not on one dimension alone, but there are interaction effects, neighboring effects between different ages, which influence mortality rates. Just as a simple example, I want to mention cohort effects. So cohort effect is an effect related to the cohort you belong to, which is just defined by the year you were born in. So it makes a huge difference for your mortality, whether you were born in 1920 or in 1980, just because of the completely different development the world has been taking since 1920 and 1980. The cohorts would be visible here in this arrangement along the diagonals. So you would see cohort effects here along the diagonal, where one diagonal might have just a very different mortality from the diagonal right adjacent to it. You might not see too much of that here in this picture because we have many ages. So you would have probably to zoom in a little bit to recognize the cohort effects in these data. But cohort effects are often present in mortality data, and there might also be other interaction effects which a CNN might be able to detect better than humans can. Another motivation is a paper by Bai and co-authors who have found that CNNs are better suited for certain sequential prediction tasks than recurrent neural networks, which is remarkable since recurrent neural networks are specifically designed for sequential prediction tasks. So, and of course, we are also given a sequential prediction task here because mortality rates come as time series. So you have a dependence on time, obviously. And therefore, we propose to use convolutional neural networks for forecasting mortality rates. And more precisely, we use a bootstrap ensemble of CNNs. So this means we do not train one convolutional neural network, but multiple convolutional neural networks on different bootstrap samples of the same training data set. This has two advantages, at least. So one advantage is that it's just a standard procedure you do to make your models more stable. Because there's some randomness involved in training neural networks, and using ensembles, so training multiple of them, just serves to stabilize the forecasts, and it also can improve the forecasting performance slightly. And moreover, the second advantage is that this will come in very handy for quantifying prediction uncertainty, as we will see in a second. I should also mention that a similar approach to this one has been successfully investigated recently by Perler and co-authors. So they use one-dimensional convolutional neural networks, and they only make point forecasts, but they show that this works quite well with the CNN methodology. And another thing that they do is they show a relationship between this convolutional neural network and the more classical Lee-Carter modeling approach. And this is also important because this improves the interpretability of this neural network model, which is an important thing for many applications. For example, if you want to apply a model in an insurance company, it usually should be a quite interpretable model, because you have to sell this to the regulation authorities and so on. So you have to be able to understand what your model is doing to some degree. And for this, we explain the analogy between the two models. So we have a fixed age, year t, age x, year t, and population I here. And then our model reads like this. So we have the log death rate equals, okay, and for this you have to understand that this is basically the equation defining the output layer of our neural network here. We have a linear activation in this output layer, so we do not have any function here. And then we have one output node per age x. So this is for a single age x here. And then we have a bias term, bx, plus a scalar product between a weight vector and the input of this output layer. And the input of the output layer is just whatever comes from the hidden layers of the neural network. So this is just a nonlinear function of the input of the neural network, and the input of the neural network are previous observations of death rates arranged in such a matrix here. So the input looks somehow like this. Okay, so this is the output layer of our neural network, and compare this now to the common age effect model, which I have shown you previously by Venn and co-authors, and you will see that it's basically the same structure. So you have the basic age effect here, alpha x, which corresponds to the bias term of the neural network. Then you have the age effects, which correspond to the row of the weight matrix here. And then you have the period effects, which correspond to these nonlinear functions, so to these outputs of the hidden layer. And this is also the main difference between the two models. So these kappa terms are usually calibrated by linear methods such as PCA, whereas these vectors here are calibrated via, or are obtained by nonlinear functions, so by convolutional pooling and dense layers. And in this sense, this model generalizes the common age effect model from the classical mortality modeling literature. So this aids the interpretation, but another thing which is relevant, which I've already mentioned, is that we should be able to quantify prediction uncertainty of our neural network model. And we want to do this by calculating prediction intervals. So we want to give a lower and an upper bound for future realization of the death rate at age x and for a future year t. And this realization should be contained within the interval with some high probability A, for example, 95%. And in order to get this lower and upper bound, we make an assumption. We assume that the logarithmic death rates that we observe are obtained in the following way. There is some true underlying death rate, which we cannot observe. We can only observe it with some added noise, epsilon. So this has zero expectation. And is heteroscedastic, so it can have different variants depending on age, year, and population. Okay, and now we want to determine how well the forecast we make approximates the observation. And we do this by calculating the expected squared deviation between the two. And fortunately, there's the bias variance decomposition, which tells us that this equals the squared bias of the estimator plus the variance of the estimator plus the variance of the noise. And what we have to do now is to estimate these three terms. And then in this way, we will estimate the expectation. And from there, it's a small step to obtaining these prediction intervals. And for this, we follow an approach from the literature for feed-forward neural networks, and we adapt it to convolutional neural networks here. So first of all, we assume that the bias equals 0. This is an assumption, and I will comment on it shortly later. Then we estimate the model uncertainty based on the variance of the ensemble. So this is where the advantage of using an ensemble comes in. Remember, the forecast of our neural network model is just the empirical average over all the forecasts of the single ensemble members. And the model uncertainty estimator is then just the empirical variance of all the ensemble members. So this is just a very natural way to estimate the model uncertainty. And what remains to be done then is to estimate the noise variance. And for this, we train an additional feed-forward neural network. And then we can define a variance estimator just as the sum of those two estimators. And then if we make a normal assumption, we can get interval bounds easily from this. So we get the central forecast plus or minus a quantile of the standard normal distribution scaled by our standard deviation estimator, which we have obtained in the previous steps. Okay, so much for the theory. And now we want to evaluate the method on some real data. So for this, we use the Human Mortality Database, which is the most well-known data where mortality database the most well-known database where mortality data are freely available. And we calibrate now all the models we have mentioned, basically. So the Lee-Carter model on 10 or 20 years of data, the augmented common factor model, the feed-forward net, the recurrent net, and the convolutional neural net we have proposed. And we calibrate on the years up to 2006 and on the full age range from 0 to 100, and evaluate out of sample on the years 2007 to 2016, on the ages 60 to 89, which are most relevant for calculating annuity values, for example, and on 54 populations. And we consider different error measures here. We consider the mean squared error, the mean absolute error, and the median average percentage error for point forecasts. So the former two we just consider because they are basically standard in the literature, and in order to be able to compare to previous literature as well. But we additionally consider this relative error measure. So here we divide by the actual death rate again to make this independent of the scale of the death rate, because the other methods depend on the scale. And therefore, they will, for example, be stronger influenced by higher ages, because death rates are a lot higher at higher ages, and therefore these will depend stronger on the performance of the models for higher ages and not so much on the performance for lower ages. Furthermore, we want to evaluate the quality of the prediction intervals, and for this we look at the prediction interval coverage probability. So we just count how often the true death rate lies in the interval we have predicted for it. And then from this, we estimate a coverage probability. And of course, this should be close to this A here. So in our case, 95%. However, we can, of course, make this arbitrarily large if we just choose the intervals wide enough. So if we just say, okay, the death rate lies between 0 and 2, then yeah, that's probably true, but it's also not very informative. So therefore, we also consider a second measure, which is the mean prediction interval width. So the name says it all. It's just the average of the widths of all the prediction intervals. And here are the results. So we have one row per model, and we have the different measures in the columns. And we see several things here. So we see, first of all, that the feed-forward neural network actually performs best with respect to the squared error. However, the CNN ranks second here. With respect to absolute errors, the CNN is best, closely followed by the feed-forward neural network. And with respect to relative errors, the CNN is clearly doing a better job than the feed-forward neural network and the other models as well. We also have that the CNN and the FFNN have a prediction interval coverage probability above 95%, which is good. The other models are clearly below that. And we also have that the mean prediction interval widths of the feed-forward neural network is slightly lower. So this model is doing a slightly better job in estimating prediction intervals, but still the intervals estimated by the CNN are reliable. Regarding the question as to why the FFNN is better for the mean squared error, but not for the relative error, we have had a deeper look into the error structure here and have found that the feed-forward neural network is better at forecasting mortality at higher ages. And just remember what I said, the mean squared error is influenced a lot more by higher ages. So this is just lower here. But if you look at younger ages, then the CNN is doing a better job actually. Also, what we found in a robustness check on a 20-year forecasting period, so for a longer time period, the CNN clearly outperforms all other models. So it might even be showing a better performance for longer time periods. And of course, longer term forecasts are also very relevant for applications in demography or actuarial science. Now let's just return to the example we started with, so the females of England and Wales, and let's see how the CNN is doing here. And we see that for higher ages, the red line, which is the CNN forecast, the point forecast, is very similar to the Licata forecasts. But for younger ages, the CNN is clearly doing a better job here and is still underestimating underestimating the mortality development a little bit, but it's very close to the actual realization. We also see that the prediction intervals contain the true value in every case for this particular population and this choice of ages. As I've said, another important thing about mortality models is the plausibility of their long-term forecasts. And therefore, we show these long-term forecasts here. So we show for all the models and for the male on the left-hand side and for the female on the right-hand side populations of England and Wales, the forecasts for 1 year ahead, 10 years, 20 years, and 30 years ahead. And for the 30-year forecast, we also show the prediction intervals on a log scale. And now we can make several observations here. First of all, we see that all the models forecast a log linear dependence of mortality rate on age. And this makes sense. This has been observed for a very long time. So this would be considered as biologically reasonable, so to say. Another thing is that most of the models forecast larger age-specific improvements for younger ages. So they say, okay, age 60, for this age group, we see a better potential for further improvement. For higher ages, the potential for further improvement isn't that large anymore, and we forecast smaller improvements generally. This also makes sense from a demographical point of view. What we also see is that the feed-forward neural network tends to have a little bit optimistic forecasts, in particular when we compare it to the ground truth. So the improvement rates implied by the feed-forward neural network for these populations are a bit optimistic, perhaps. And finally, we also see that the recurrent neural network is behaving a bit peculiarly when looking at younger ages with respect to its prediction intervals. But one has to say that when we remember the results, the total results, the recurrent neural network wasn't doing so well here regarding all error measures. So perhaps this isn't the best model choice here at all. Apart from that, the long-term forecasts for all the models look quite plausible. And with this, I would like to conclude and mention that there is still some potential for further improvement, even though we have seen that the CNN is doing quite a good job. So first of all, more on the theoretical side, it would make sense to check some of the assumptions we made for evaluating the prediction uncertainty. These assumptions are a normal distribution assumption I have mentioned, and also that we assume that the out-of-sample bias of our estimators is close to 0. These assumptions are somewhat justifiable ex post because we have seen that we get reasonable prediction intervals. But of course, it would be interesting to perform a theoretical investigation as to what would be the consequences of a violation of these examples, and how we could check if these examples can be regarded as fulfilled for a particular application. A second point is that we have seen that feed-forward neural network and convolutional neural network perform both quite well, and perhaps they perform also well on different parts of the data. So for example, we have seen, or I have told you, that the feed-forward neural network performs better for higher ages. the CNN performs better for lower ages. So perhaps it would make sense to use their forecasts as an input for a new model, a so-called meta model or meta learner. And this model gets the two forecasts and perhaps some additional information. So for example, I want to forecast mortality rates for age 65 in England and Wales for the year 2016. And then the model has to decide, okay, do I trust the feed-forward neural network more or the convolutional neural network in this case? And then you would calculate a weighted average of their forecasts and in this way obtain an improved forecast for mortality. And this procedure is called stacking and would be interesting to investigate here. And finally, of course, as I've mentioned, explainability is an important point here. And we have done some efforts in this direction, but it would also be interesting to do a little bit more here. So for example, one could adapt the SHAP algorithm for further investigating the explainability of the CNN and having a look at the reason of why the CNN makes a particular forecast for a particular population. If you want to know more details on this, you can have a look at our preprint. You can contact me directly, or you could ask a question right now. Thank you.
Thanks a lot for your talks, Simon. And other questions from the audience directly? So let me maybe put a very provocative question. If you look at the prediction intervals of the classical models, then we see that they are far away from doing that what they are supposed to do. Is it still possible to rely on the traditional models then?
You mean because the coverage probabilities are a bit low here? Yeah.
They are slow, and the MPIW is also slow. So it's not that they have a high variation. So they will stay there at the coverage probability.
Yeah, I have to admit that there is also a source of uncertainty which is not really covered in these prediction interval coverage probabilities, which is parameter uncertainty. And it's just the reason for this is that the usual standard approach for calculating prediction intervals for these models is to not include it. But of course, you could include it, and then you would perhaps also increase the prediction interval coverage probabilities somewhat here. Apart from that, if you're below the required prediction interval coverage probability of 95% here, then yes, the model is not ideal. I would agree with that.
Okay. More questions from the audience? As Simon said, you can still send a mail or ask a question later. So that's always possible for all the talks. So if there is no more question, I don't see anyone in the chat. So let me thank you again, Simon, for this nice presentation.
Thank you.